In this video, we introduce u-substitution, which is primarily a tool for working the chain rule backwards when we're getting an antiderivative of a composite function. And the goal with this video is to give a quick by-example overview of the key points rather than a formal theoretical discussion. So we start with an example, and I want to demonstrate this example with 3 different levels of formality. And in the first level of formality, I'm just going to say, okay, x cosine x squared, I'm trying to get the antiderivative of this thing. I think it's pretty close to saying sine x squared. And the reason why is because the chain rule should produce a factor of 2x out of that, and that gives me basically what I started with. So this is kind of a guess and check and adjust kind of method. And when I differentiate this guess, I take the derivative with respect to the argument, and that gives me a cosine x squared. And then the chain rule tacks on the derivative of x squared, which is 2x. And I basically have the integrand I started with. It's just there's an annoying factor of 2 that appeared because of the chain rule. So what I'm going to do is adjust for that by throwing a 1/2 into this function, a 1/2 sine x squared. And now when I differentiate that 2 from the 2x is going to cancel the 1/2 out in front, and I'll get an x cosine x squared. So we're good. Don't forget your plus c. So another way of saying what we want here is that I'd like to get the derivative of the interior function sitting right next to the composite function. So this is a way of highlighting the chain rule backwards. So in my next method, and this is pretty close to how most people handle integrals and differential equations, physics and engineering, I'm going to just build that derivative right next to the cosine function. And of course you can't get away with just throwing 2's around, but I could compensate with a 1/2 out in front. Just keep in mind that constant multiples can move in and out of an integral, but variables can't. And there I have it. I have a composite function with the derivative of the interior function sitting right next to it, showing me exactly what the chain rule has done. And I can just guess that this came from differentiating the sine of x squared. Finally, we introduce the formal u-substitution. And this is just a way of symbolically transforming the integral to account for the chain rule. What we want to do is express the interior function of this composite function as a u, and then express the integral with a differential of du instead of dx. And finally, we'll compute the u integral and then transform the result back in terms of x. So in this case, we're going to let u be x squared. And then I have to get at the differential dx here. And so I'm going to take the derivative du dx, and that's 2x. And that allows me to relate the differentials of u and x. So I multiply by dx on both sides and get a 2x dx. Now there's 2 basic paths that I could take from here. One way to finish this thing is to build that differential 2x dx inside the integrand. And the only reason this is possible is because I happen to have the correct variable piece there. That's the x that's out in front. And this seems familiar because it's basically the same thing that we were just doing in that second integral. So I multiply by 2 on the interior, multiply by 1/2 out in front to compensate for it. And I've built my 2x dx, and I have a name for that. That is du. So I replace the x squared with a u, and I get cosine u. I replace 2x dx with du, and I have a cosine u du. And now I can simply guess the antiderivative of the cosine, which is a sine function. And I'm not done yet because it was an x integral, and I better have an x answer. And I get 1/2 sine x squared plus c. So same answer as before. Now the other way I could handle the transformation of differentials is to actually explicitly solve for dx. And that would give me a du over 2x. So taking my original integral and replacing dx with du over 2x and replacing the x squared with a u inside that cosine function, I get here. So x cosine u du over 2x. And again, the only reason this works out is because we had the correct functional piece in here to give me the derivative of the interior function. If I didn't have that x tacked on, this wouldn't work. If it was an x squared, this wouldn't work. So the reason this is working is basically because I was set up to do the chain rule backwards. So that 2 in the denominator comes out in front, and I have a 1/2 integral cosine of u du, and we get to the same place. 1/2 sine u plus c, and replace the u with an x squared, and I get 1/2 sine x squared plus c, and we're done. Now, before we move on, I want to point out that it's easy to get lost in the formalism when we're doing an explicit u-substitution. So that third integral, the way I do it, I would call that an explicit u-substitution. Ultimately, it's better to solve the integral like the second approach. So we're trying to see the chain rule backwards by seeing the derivative of the interior function tacked on to the integrand. So even if you elect to use an explicit u-substitution, it's not going to work unless you essentially have the derivative of the interior function sitting there in the integrand, because we're doing the chain rule backwards. So that's usually what we're looking for before we launch into a u-substitution. Now let's take a look at how to do a definite integral that involves the chain rule backwards. And in this one, the interior function is a polynomial, and that's being raised to a power of 4. And then the derivative of the interior function is essentially provided to us in the integral. That's the x out in front. Now the derivative of that interior function is actually negative 2x, but we can adjust for constant multiples. And again, we take 3 approaches to the integral. So in the first one, I'm going to take the informal approach of constructing the derivative of the interior function in the integrand. And the derivative of that interior function is negative 2x. So I multiply by negative 1/2 out in front and negative 2 inside the integral to compensate. And now I have a function raised to a power, so 3 minus x squared raised to the 4th, sitting right next to the derivative of that function, which makes it clear how the chain rule is operating. And I'm able to guess the antiderivative. So I have this function raised to a 4th sitting next to its derivative, and I use the power rule on this, and I get 3 minus x squared to the 5th divided by 5. And we still need to evaluate that as x goes from 0 to 1. Now, before I do the evaluation, because this is an informal method, I'm going to check that that antiderivative actually made sense. So if I differentiate that thing, move the 1/5 out in front there, it would give me a negative 1/2 times 1/5, and then differentiating 3 minus x squared to the 5th with respect to its interior, I get 5 times 3 minus x squared to the 4th. That's the power rule for derivatives, multiplied by negative 2x. That's the chain rule. My 5's cancel, my negative 1/2 and my negative 2 cancel, and I'm left with an x times the quantity 3 minus x squared to the 4th. So we've done everything correctly. Now what about evaluating this thing across the limits of integration? I have a negative 1/10 after I gather the constants. And then when I sub in a 1 into this thing, I end up with a 3 minus 1, or a 2 to the 5th. And when I sub in a 0, I end up with a 3 to the 5th. So I have a 2 to the 5th minus 3 to the 5th. And this works out to 211 tenths, or 211 over 10. In the next approach to the integral, I'm going to use a formal u-substitution. And as usual, we're going to say u is the interior function. So we're going to let u be 3 minus x squared. And then we take the derivative of that to get du dx. That's negative 2x. But we multiply both sides by dx, and we get that du is a negative 2x dx. And this time, I'm going to opt for building this differential, negative 2x dx, inside the integral. Again, keep in mind, this is only possible because we had the right function piece in there. We had that x in there, making it so we could build the derivative of the interior. And of course, I can't just multiply things by negative 2 whenever I want. I have to compensate by putting a negative 1/2 out in front. And now the negative 2x dx, that's du. And the 3 minus x squared to the 4th, that's u to the 4th. So I end up with a negative 1/2 integral of u to the 4th du. And then I have to be careful about my limits of integration because those are x limits of integration, and I'm going to label them that way. I'm integrating as x goes from 0 to 1. Now, the whole argument for doing explicit u-substitution is that it makes it easier to guess the antiderivative when I get to that point in the problem. So u to the 4th has a very easy antiderivative. It's 1/5 u to the 5th, and then I'm evaluating as x goes from 0 to 1. And this means I better transform my antiderivative back in terms of x. So u was actually 3 minus x squared. And now I'll just write that my limits of integration are 0 to 1 because I'm back in terms of x here. And this is the same expression I had before. When I sub in my upper limit, I get a 2 to the 5th. My lower limit gives me a 3 to the 5th. And when I clean things up, I get 211 over 10. Now, the reason I wrote down a third version of this thing is because we actually have an option to transform the limits of integration into u space, and then we can forget about x. So all the substitution is the same here. I'm going to go ahead and bounce to this step from the previous version of the solution. I have a negative 1/2, and I have the integral as x goes from 0 to 1 of u to the 4th du. But instead of guessing an antiderivative and transforming it back in terms of x, I'm just going to ask myself, when x is 0, what's u? And I go back to where I originally defined u, and I plug in x equals 0, and I find that u is 3 minus 0, or 3. So my lower limit of the integral then becomes a u limit of 3. Then I ask myself when x is equal to 1, what's u? And u is going to be 3 minus a 1 squared, or 3 minus 1, or 2. So now I have negative 1/2 integral from 3 to 2 of u to the 4th du. And I guess the antiderivative, giving me a 1/5 u to the 5th. And I'm going to evaluate this as u goes from 3 to 2. So the cool thing about this approach is that it allows us to forget about x forever. So we just completely transformed the problem into u space, and we're going to get our final number out of u space. So I have a negative 1/10 out in front. And when I plug in the upper limit, I get a 2 to the 5th. I plug in the lower limit and I get a 3 to the 5th. And that simplifies to 211 over 10. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.